So these are like kind of points that are as independent as possible. And then there are other kind of processes of a very different nature. So for instance, you can, if G admits a lattice, so here consider some locally compact group G, say unimodular. And if it admits a lattice gamma, then you will have a fundamental domain, say denoted by omega here, which on which the Haar measure is finite, so you can normalize it to be a probability measure. Then you can sample a point from this fundamental domain and conjugate the lattice. And this way, you can visualize lattice points also as a point process in G. And if you think about these two kinds of examples, they're really very different. So the Poisson points or this Bernoulli point process, they are kind of very independent. In particular, if you want to say in a region, you want to count how many points are there, it's almost trivial because they're by definition, you know what is the distribution of points in any given region. But for lattice points, it's very difficult. Actually, counting points is a very challenging question if you ask for the optimal counting. So somehow, in some aspects, the random points are easier to deal with. And it's kind of will be very, very nice if you can relate these two. And indeed, it has been done in some ergodic theory context. For instance, in the theory of cost, there's a recent breakthrough by Frajic, Malik, and Wilkins that they somehow solved the fixed price one conjecture for higher rank lattices utilizing the Poisson points. So somehow, but not much is known. It's kind of a new line of thinking to relate lattice points to some genuinely kind of independent point processes. Okay. So in more ergodic theory context, point processes actually have been considered for quite a long time. It's usually in the language of taking cross sections or things like that. So here, it's a kind of, if you consider some, say, non-discrete locally compact group, and its probability measure preserving action on some standard probability space, then kind of, you in some context, you want to take a certain discretization which preserve the dynamical properties. And so it turns out that point processes is a good way to think about such a problem. In the thesis of Sam Malik, working with Miklos Abert, they show that actually every PNP action of a locally compact second countable unimodular group can be seen as a point process on G. And this is really, it's kind of philosophically a very good thing, because now you instead of thinking abstractly across sections and how to discretize, you really think about points on G, and then certain tools kind of dealing with discrete things you can apply to non-discrete group actions. And then later it was kind of they studied the cost of actions and some other notions, and leading to a lot of great results. So this is some background why people in ergodic theory also care about point processes. So here, what we are trying to consider is metric properties. So the study of lattice in semi-simple Lie group has a very long history, and if you have a co-compact lattice, then your fundamental domain is compact. So the metric structure of gamma is really pretty much the same as G. It's like the perfect discretization in some ways. But if you take a non-co-compact one, we can see it as points on G. Then you see that because the fundamental domain is not co-compact, you can imagine some cusp and some other shapes. Then as points, you can see that there are very big holes between the points. And sometimes you can even kind of look at infinity and see some big gaps, so some kind of patterns at infinity. So, and then if you think about a point process, like Poisson points on G, then you can kind of imagine that it's neither co-compact nor in this kind of cusp situation, because if the process is invariant, then you are not going to truly develop a cusp set infinity. However, you do have big holes kind of in between points and are actually quite arbitrary local patterns. So this makes the metric structure quite interesting. And you can consider the following question. Take, say, a constant intensity, so invariant Poisson point process on G, and then you restrict the metric on G to the points, so you induce the metric. And you can ask how much this kind of discrete subset with induced metric inherit the metric structure of G. So kind of do you have a certain kind of behavior similar to lattices in some ways? And in this regard, so we're going to study this question up to quasi-isometry. So first, just remind you the notations for quasi-isometry. So here we have two metric spaces and the multiplicative constant kappa. So this is the kind of the more important constant, and the additive constant C. So if you have a map from X to Y, we say that it is a quasi-isometric embedding with constants kappa and C. If in the image space you look at the distance, then it is controlled by these two affine functions with the constant kappa multiplicative and C additive. And if in addition that you are almost onto, so every point in Y, you can find an image point of X within distance C, then we say that V is quasi-isometry. And in this case, you will say X and Y are quasi-isometrically equivalent. So these are kind of standard notations. And then given some point process of, so in the study of quasi-isometry of groups, usually if you can figure out what is the self-quasi-isometry group, then you solve almost everything. So for point processes, you can ask a similar question: what are the self-quasi-isometries? And there's the question of Miklos Abert. I think it's quite a clever question because it doesn't quite make sense for lattices. You cannot take two independent lattices, but for point processes, you can take two independent samples, and you can ask, are they quasi-isometric almost surely? So this is somehow a question you can only ask when you have a measure. You take two copies and ask, can you match them up? And quite surprisingly, I still find it's a really amazing result that in R, if you take two independent constant intensity Poisson processes, so just you take two samples, then Basu and Sly back in 2000, the paper came out 2012, that they show that you can indeed find the constant kappa and C such that almost surely two independent Poisson processes on R, they are kappa C quasi-isometric equivalent. And the proof of this uses some very intricate multi-scale analysis. So you have two independent copies and you want to somehow match them up on all scales. And it's kind of, you have to consider like, really really a multi-scale analysis in order to show such a QI exists. And later, together with Sidorovic's, they extend the result to higher dimensions. I'm not going to state it here. And for the and they also have a result for Bernoulli P points on Z. And they show that if you take two independent copies, then there exists a capacity, not by Lipschitz embedding from one into another. I didn't figure out if they are by Lipschitz equivalent or not, but they show there's a Lipschitz embedding from one copy into the other. So for Poisson point processes on R, you can have these quasi-isometric equivalence between independent copies by this result of Basu and Sly. And then the next natural question is what happens on trees? So you take a regular tree and then take an independent Bernoulli P point process on it. Then you can ask if you take two independent samples with induced distance, are they quasi-isometric or not? And if I understand correctly, this question is still open. There is some evidence in the positive direction. So this result announced by Athrea and Trotsky, they show that if you take Gaussian-Wilson trees with some assumption on offspring distribution, so for instance, they need to be bounded offspring distribution, maybe some other mild assumptions. Then if you condition on the trees being infinite, then two independent copies are quasi-isometric almost surely. But if you, so this is kind of evidence that you can match up one connected component with an independent one. But then the question on the full tree is still you have to you have so many components, is it possible to slide them around and match up? So this is still very complicated. So then so these are results where things are kind of flexible. So if you think about how is it even possible to match up two independent Poisson processes on R, is somehow you're allowed to slide and find your good match. And on the tree, there's something kind of working in similar ways. You'll be able to move things around and try to match up configurations. So this is some kind of flexibility of the space. And you can ask in what context do you expect to see some rigidity that you're not able to come up with very flexible quasi-isometries. And it's kind of very classical that in hyperbolic geometry, H2 is considered as flexible. This is manifested in many different ways. But in higher dimensions, starting from H3, you have the celebrated Mostel rigidity. So that's a place where you expect to see some rigidity, but we haven't figured out what exactly happens to Poisson points on H3. Hopefully we can make some progress on that later. But if you go beyond rank 1 spaces, then it's kind of it's usually considered the higher rank situation is even more rigid. And for study of lattices, you have these kind of very well-known QI rigidity results in higher rank symmetric spaces. In 1907, Kleiner and Lieb proved rigidity theorems for QI in higher rank symmetric spaces and Euclidean buildings. And the results also establish a complete classification for co-compact lattices in higher rank Lie groups. And so this is for co-compact lattices. For non-co-compact lattices, the first significant result was due to Schwartz. So he showed a very complete classification under QI for non-uniform lattices in rank 1 semi-simple Lie groups, excluding this flexible case SL2R, whose symmetric space is exactly the hyperbolic plane. And his main tool is to look at these kind of CASP boundary patterns and show that under some QI, you have to map them in certain ways and obtain very strong results. And then later, Eskin gave a complete characterization for QI between non-uniform lattices in higher rank Lie groups. So in particular, if you take a simple higher rank Lie group, then non-uniform lattices are actually arithmetic by Margulies' theorem. And he showed basically the QIs, they're more or less commensurators. So they have very specific structure in this context. So this is kind of, and then there are a lot of other QI rigidity results not going to survey here, but this work of Eskin is the most relevant for what we study here. So what we consider here is the kind of a pure rank 2 phenomenon. So if you believe that one regular tree is somewhat flexible, at least this Gaussian-Wilson tree result tells you that for connected components, you can really try to match them up in QI. But if you take two copies of it, so tree is the free group is the lattice in SL2R, so you can think of it as a rank 1 non-uniform lattice. So it's kind of a rank 1 flexibility there. But if you take a product, then your rank becomes 2, and then you start to see this kind of higher rank rigidity phenomenon. And here, if we take a product of two regular trees and take two independent copies of independent Bernoulli P process with the induced metric always, then almost surely there is no QI embedding from the first copy to the second. And since there's no QI embedding, of course, they are not QI equivalent. And this is kind of the product of two trees is maybe the least rigid in higher rank situations, right? Because there's no property T and each factor is rank 1. So we expect a similar phenomenon to hold in more rigid cases, namely other more general higher rank symmetric spaces or lattices. But we chose to do this particular case with, otherwise the language is a lot more complicated. But the point is to show this phenomenon that in rank 2, you already observe this kind of, you cannot make arbitrary QIs, kind of, you have less freedom to match up things. So, and we also show that if you consider self QI, so, you just take one copy and consider what kind of QI embeddings it can admit back to yourself. So you always have the trivial one. You just take the identity map, and then you want to know if kind of a QI embedding should be close to just the identity map. You really don't have the freedom to move points around. And here we show that it is the case up to some kind of a field of random errors. So this I call it the stochastic wobbly. It's like you can move around depending on where you are a little bit, but not too much. So here the statement is that there is a measurable map. So here its notation is not too easy to read. So basically you take in a copy, take in your point process marked with the point X. So it's a pair D, and then X should be in D, more or less. And then given that point, you look at your configuration, and then there is this radius R, which is kind of, it depends on the points and depend on where you look at this point configuration, but it is invariant under automorphism. If you move it to anywhere, somewhere else, like the whole thing move to another place, then it reads the same radius. And so this is kind of a field of errors that you can possibly admit. And then, so there is such a random variable, and for any self quasi-isometric embedding with a given constant, there is another possible additive constant, so that where you can move to is bounded from above by this random variable, possibly plus another additive constant. So it's kind of, so if without this R, you just say that this is, you can only move by bounded amount, then it's actually trivial. It's really kind of within bounded distance to the identity map. So it's a kind of trivial in the QI group. But here you do need some error term because the point configurations, they have arbitrary local patterns. So, imagine that somewhere you have quite a big hole, inside it only 2 points, then you will be able to swap the two under the QI. So because of these local fluctuations, you do need this additional kind of a field of possible additive error terms, but you cannot move them too fast. So the point is that it's really controlled by this all these kind of wobbling constraints, and you're not able to make like multiplicatively something different. You just move around what is allowed at a given point. And this random variable R, we didn't kind of look too closely on its distribution because we used some quasi-flat theorem as a black box, and there is a lot of constants that's not specified. So, but we think that it should be quite tight, so should have exponential decaying tail upper bound. So the chance that you move more than distance R should decay exponentially in R. So you're really in a quite tight situation. So these are the two statements we have. So it tells you that in this rank 2 phenomenon, rank 2 situation, you already have a lot of constraints, and also because the points the random points do not have inherently like some translation structure or any, arithmetic structure or anything. So you simply will not able to find the non-trivial symmetries to map D back into self or something else. Okay, so any questions so far? So okay. So
All right, can I ask a question?
yeah.
So in your quasi-isometric embedding results, those are factoring through these Fisher-Eskin quasi-isometric invariants, quasi-isometry embedding invariants, or something else?
We don't use the Fisher-Eskin. We don't look at invariants. So the proof is you'll see the proof. It's basically we detect some specific structure that this phi must satisfy, and then you just argue in the end that you cannot match up holes in the random configurations if yeah, so we don't have we do not really look at QI invariance or anything structural. It's really that we show that if you consider a QI embedding, then it must have some splitting structure, and then it boils down to some elementary count.
Okay, thanks.
Yeah, it's not and it's really because the points are kind of because of the randomness, you are not able to move them far away, or there's no real symmetry on these points. So
Great, thanks.
okay, so see, I'm doing with time. Yeah, so in the remaining time, just sketch the proof. So as we mentioned before, there is this celebrated paper of Eshkin in 98, where he classified non-uniform lattices in higher rank Lie groups. And the proof, it starts with some kind of with this embedding of flat into, you consider QI embedding of flat into the symmetric space. And there, if you consider if you start with a non-uniform lattice and look at kind of what points are near a flat, then you see it's quite a big, it actually looks quite like a random configuration, right? There are holes and it's kind of quite inhomogeneous. And it turns out that this proof strategy can be implemented for Bernoulli points, or if you consider Poisson points, it will be quite similar. That this kind of consideration also applies to random points. So we follow the proof scheme of Eshkin for non-uniform lattices. So the main tool is called this quasi-flats with holes. So it tells you exactly what happens to a flat if under this kind of QI embeddings. So here we're in this simple situation of a product of two trees. And then a flat there is just you take one by infinite geodesic from each tree and make a product, and that gives you a copy of Z square embedded isometrically there. So it's kind of, you can think of this as a flat in this case. And then we are given these points D, and you can look at which the intersection of the point process with F. So you'll see it's actually just a Bernoulli P point process on F itself. And then you want to know under this QI embedding that we want to study, where do these points go? And it turns out that if your point configuration is sufficiently regular, then there is this theorem called the quasi-flats with hole theorem that will tell you that you must be mapped near finitely many flats. So here the key point, or the key notion of being sufficiently regular is this kind of a quasi-center. So yeah, I cannot draw it here, but you can see what is the definition. So you're given a bunch of points, a set of points U, and then you look at this point configuration from standing at X. And then we think of X as being kind of epsilon rho quasi-center of this set. If for sufficiently far away points, namely points that are rho away from X, then for such a Y, so it's sufficiently far from X, and then you take epsilon times the distance ball around Y. So it's kind of graded in this way that it's always epsilon times the distance to x, and then you count how many points do you have in that ball, the U points. And then you want to have sufficiently many points. And here the requirement is that you have 1 minus epsilon proportion of that ball all included in U. So this, if this is true for all sufficiently far y, then we say that x is the epsilon rho quasi-center of U. So these are actually the points that behave well under these QI embeddings. So this is kind of a key notion from that theorem. And then so that was the starting point of Eshkin's argument for non-uniform lattices. It was called the quasi-flat with holes theorem, established in Eshkin-Fab, and for higher rank symmetric spaces. And later, Wortmann generalized it to kind of these buildings and other notions of like the building symmetric spaces of reductive groups later. But it tells you the following thing. So it's also known as how to embed the Swiss cheese. So the picture is that you have some like a flat, and then your points can admit big holes. But however, if you're in the case where this set of epsilon rho quasi-centers are non-empty, this set is non-empty, then there is a constant M1 that only depends on the multiplicative constant kappa, such that so we can maybe I do not read all the quantifiers, but morally that if your set has these regular centers, then for every quasi QI embedding with the constants kappa c, you will be able to see that these good points are mapped near a neighborhood of a union of at most M1 flats. So that tells you that you map one flat, you look at this embedding of one flat, and the good points have to be close to a union of finitely many flats with a uniform bound on how many you have. And there are examples showing you that in general, you can have quite complicated situations. You can say map one flat into 3. That's kind of quite typical things to construct. So looking at just one flat like this, you cannot rule out that M is some kind of a constant not equal to 1. And so the beginning of maybe just say a remark here. That sometimes it's convenient to extend your map from a subset U to Z square, and because there are big holes in this situation, if the set U satisfy this epsilon rho quasi-center is non-empty, then you can extend naively this map by saying if you have a point Y far away, then you maybe adopt the value of one of those points in your epsilon dxy ball. And in this way, if you extend this way, then what you get is what's called a graded QI embedding, in the sense that it looks like a QI embedding, but however, your additive constant is allowed to depend on distance, so you can potentially grow like epsilon times the distance. And this is kind of inevitable in these situations with big holes. So in the proof, we have to kind of keep track of all these graded constants, and that created some complications. But this is kind of have been studied in several contexts of these graded QIs. Okay, just a remark here. And so the proof goes like this. So we start with some point configuration D. And first you want to regularize it a little bit. So basically what you can do is to take this what Schwartz called the neutered space. So you take D and then you fatten it to some neighborhood with additive constant n epsilon. And here you choose a sufficiently large n depending on epsilon. So you kind of make your set fatter, and then you just extend your original QI embedding. So here we are considering, I didn't write it. So the context is that we consider a QI embedding from D back into the product of two trees with the specified constants kappa and C. And then you choose some sufficiently small epsilon and fatten it up first. And then given a flat, you can consider now in the flattened process, this the intersection, which points are there. So the point, the reason for doing this flattening is to make it easier to check that this point configuration satisfies the assumption of the quasi-flats with whole theorem. So you do have non-empty quasi-centers. And you can also repeatedly take a quasi-centers. It will be useful later, but not going to talk too much about it. And then once you satisfy these assumptions of the theorem, then it gives you that your flat should be mapped to a neighborhood of a union of constantly many flats. In the next step, you want to rule out the possibility that you're in this complicated situation that one flat goes to, I don't know, 6 different flats and in some complicated way. And so just like in Eshkin's original proof, the way to consider this is to take 2 transverse flats. So here you take transverse here means that you say in the first copy of the tree, you use the same line. And then in the second copy, you take 2 lines that only intersect at one point. Then you get the 2 flats which intersect at a singular line. And then there is this with some kind of geometric considerations. So it basically tells you that if you are standing on this singular line, and this point is sufficiently good in both flats, then from there you can show that this particular singular line, it should be mapped near one singular line. So here this notation is that seen from the image of X, the Rostov distance between these 2 lines, if they grow like with this graded constant sum multiple of epsilon. So they kind of, because you cannot really say that at this moment they are within bounded distance, but it kind of grows like in this controlled graded manner. So this is the more involved part of the argument, but it more or less follows the same reasoning as in the symmetric, as in Eshkin's proof. Okay, so now once you have this singular line to singular line, then it allows you to show that you have a well-defined boundary map. And so here, because we need to argue like almost surely into some probability calculations. So here we take a countable dense subset of points in the product of 2 tree boundaries. And then with this singular line to singular line argument statement, one can show that there is a well-defined boundary map. It basically takes one chamber, and in a chamber, you can think of it as with kind of lined with these singular lines. And if you know where the singular lines go, you can see that the image of one chamber is it can only be near one chamber. So you're not in the situation of one flat map to many different flats. And this way you get a chamber to chamber map. And it's this kind of since this product of 2 tree boundaries is actually the Furstenberg boundary of this product space. So it's kind of map is called a boundary map usually. So it's a chamber to chamber map. And then this map actually, it splits just because of the tree structures in each copy. So you can show that if you want to figure out where a chamber goes, so the chamber is like this quadrant thing. And so it has to be that you map one geodesic ray into one ray, maybe up to permuting the 2 factors. So you have one ray mapped to like you do not need to look at both coordinates. If you have a chamber, you look at the coordinates of one kind of rays, then it determines itself where it goes to. And then the second ray also have another map phi2 to tell you where it goes. So the boundary map actually factorizes as kind of in these 2 coordinates. And also using the geometry of the trees, you can show that these phi1, phi2s, they are holder by holder continuous. So it's possible to extend from this countable dense set to the whole boundary, but we are not really going to use that. And this splitting structure is really the key here, because we do not expect more rigidity after this. Once you have this factorization, then phi1, phi2, they can be individual quasi-symmetries of the tree boundary, and we know that these are they're very flexible. So somehow this splitting is the only rigidity we rely on here. So that's kind of reasonable, because we take a product of two flexible things, and after splitting, then we do not expect more constraints. And so this is the this is actually the traditional way of doing this kind of rigidity argument. You try to push it to the boundary, and then you detect some structure on the boundary, and then try to pull it back. And here to pull back the boundary map, we use the natural idea is to if you want to know in the interior where a point goes, then you can use two good flats such that they touch exactly at this point X. And if you know where each flat goes, then if you know F1 is mapped near F1 prime and F2 mapped near F2 prime, then your image of X has to be kind of pinned near the intersection. And that's exactly how we pull back the boundary map. And with some argument, we kind of, so this splitting of the boundary map will give you a splitting in the interior. And it says that if you consider a QI embedding of D into this product, then you can find two honest QI embeddings of trees themselves. So the reason is, this D itself, it has a lot of holes, but once you project to one individual tree, you actually cover the whole tree. That's why these phi1, phi2, they're naturally defined on like the whole tree. And one can see that these are honest QI embeddings. And once you, you up to swapping T1 and T2, in the interior, you also have this splitting structure that phi x is near this kind of phi1 of x1 and phi2 of x2, so exactly the same kind of splitting. And then this additive error term kicks in just because somehow so the map, all the previous argument, the more precise information are about these repeated quasi-centers. So you only say, starting from that quasi-flats with hole theorem, you only have good understanding where these good points go. And then the rest of the points you extend by triangle inequality or something like that. And that explains why there is naturally some additive error term, just because we only know where regular points go. And so it gives you this splitting structure. And then there's these two theorems that I said in the beginning. They are more or less deduced from this structure. So just to explain, it's by kind of elementary counting. So suppose that you consider two independent copies, D1 and D2, and then you want to show that you cannot make a quasi-isometric embedding from one into the second. You first, using this thing, and let's ignore this R variable and think that there are sufficiently many points, like most of the points, they actually have to be within bounded distance. Then you first enumerate how many possible individual QI embeddings you can have for each tree. And it's on this order because there are Q to the R points in radius R in this Q+1 regular tree. And then each point you basically have constantly many choices where you can go, you do it recursively. So in total, you have the choice for this pair phi1, phi2 is roughly this order. And I'm not being careful with the constancy here because there's a lot of room to spare. So it's roughly like this. And then if you go back to this product, so in the product, you expect to have like a exponential to the Q to the 2R number of points. So it's like a lot more points than the number of choices here. And if you take a sufficiently sparse net in the points, then you see that if for any given choice of phi1, phi2, because of the independence, there is a non-trivial chance, some constant chance that the given map takes it into a hole in D2, and then you just then you fail to be a QI embedding. So just because this reasoning, you see that there are way too many points to arrange for this number of possible choices. So a simple Borel-Cantelli lemma allows us to conclude that you cannot have a QI embedding from one copy to another. So it's just this splitting structure more or less gives you that. And then similarly, if you consider self-QI, then you need to be a little more careful because you need to, since we are looking at the Bernoulli point process, you need to move sufficiently far away to gain independence. But it's a similar idea. So if your self-QI attempt to move too far, then you again have this picture that you're trying to match up independent configurations, and you only have this splitting structure prevents you from too many choices. So again, this kind of but like the possibility of mapping good points into holes will prevent you from having these kind of QIs that move too far away. So yeah, in the end, it's all this elementary counting that gives us contradictions. And yeah, that's all I have for the slides. Thank you.
Okay, thank you. Let's thank our speaker. And let's start the discussion. So are there comments or questions? Well, you mentioned this in passing. So what about, hyperbolic three space or rank one symmetric spaces and the Poisson point process?
Yeah, this is something we're hoping to work out, but I think H3 is maybe the most interesting case. Yeah, so I would believe that one should have some Mosto rigidity type of results there. Yeah, so should kind of this phenomenon should be extended to Poisson points as well. Yeah, and then the other rank one spaces like I don't know, SPN1, they should be even more rigid. So.
And what about the higher rank situation? I mean, you said, I mean, this product of tree in some sense is, the first type of sort of a higher rank space, right? Where you have this kind of rigidity phenomenon. Yeah.
So right, if you take say I don't know SL3R for instance, then the same line of argument following Eskin's proof would get you somewhere kind of you'll be able maybe to get an induced boundary map, and there you would be able to say a lot more about the boundary maps. Just because you can, if you have certain regularity, you can apply, say, some rigidity results. Going back to Titt's theorem about what kind of this kind of Holder continuous boundary map can be, you might be able to see that it's even more rigid than this. Yeah.
So is this work in progress or?
I don't know. It's because it's the language is a little heavy. If you want to
I
write
mean, it
yeah,
uses, of course, this whole
symmetrically.
building
Yeah,
language.
It's, you have to adapt the language, but here it's very straightforward what the flats and the singular lines are. In symmetric spaces, you have to discuss the shape of polyhedra and other things are more involved to consider. But I would believe that's similar. Yeah, for simple Lie groups, the symmetric space should have even more rigid geometry than this. Yeah. So here only this splitting already gives us some non-trivial consequences. So in more rigid situations, they should be, but I do not know what the kind of new phenomenon might occur. Like, the reason that you cannot have QI between independent copies is maybe you have too much constraints on what the map can be, and then you cannot match up holes. But maybe there is something deeper there that one can extract from it. I'm not so sure what to formulate here.
Are there other comments or questions?
Yeah. So can I ask, I mean, in response to your answer to his question, so I guess I'm a little confused when you said that this might be useful for understanding the rank one case. Like it seemed like you were leaning hard on understanding um, the structure of quasi-flats inside the higher rank symmetric spaces, but like I mean, I guess there is a structure of quasi-flats inside one-dimensional spaces in rank one, but they're much more degenerate. I mean, is there
Right.
can you just use that there? Just, I mean, straight what you get from Moss to the Morse lemma, or like,
So
um,
in rank one, would imagine that to get the induced boundary map, you rely on more direct geometric arguments like in Morse lemma that you use like exponential divergence of geodesics, and you cannot map to two strange shapes and so on. Yeah. So right. So you do not need like a quasi-flats lemma in that case, I guess.
okay, and can you just say again in the higher rank case? So which cases can you treat and what can't you treat? I mean, like you were using Wortman, which is like in the S arithmetic case and the buildings, like so like
So
what's the scope of your theorem? Or could you re-put up? I showed up like a minute late, so maybe I missed it at the beginning, but
yeah, so the thing is that we only wrote it for this particular case of a product of two trees, and we just because if we're kind of probabilists and we do not want to make things too complicated with the language of symmetric space, and so this conjecturally you can extend such a result to other higher rank symmetric spaces, but we didn't write down in good exposition or anything. Yeah.
I see. And what
It
about
would
in
surprise
the
like
irreducible case? You think that your arguments might work also, or you need the fact that it's a product here, or
no, no, it's like we discussed in simple, say if you take a higher rank simply group, the symmetric space should have more rigid geometry than product of trees. Yeah, yeah,
right,
a lot
right.
more rigid actually. Yeah.